All right, guys. Lesson 5, part 4, Sum and Difference Identities. Let's do this. So, sum and difference refer to a trig function where the argument has two terms, two angles, alpha and a beta. So that's what the sum and difference refers to inside the argument of a trig function. If you see a sum or a difference, the first thing you should think is this identity family. So this is what's going to apply. It's also going to allow us to extend our knowledge of exact trigonometric values. So far, you could estimate any trig value with your calculator by plugging in the value. But knowing them exactly is exclusively the domain of the unit circle. If I were to tell you what is the exact value of sine of 30, you would say 1/2. I'd say, what is the exact value of the cosine of 3 pi over 2? You'd say, anyway. So we know values on the unit circle exactly. The sum and difference identities allow us to extend that knowledge of exactness to several more values. Reduction identity. So this is something we don't cover a lot here in this section, but next section. So it's kind of curious that they include it here. Reduction identity is when the exponent of a trig function is reduced by an identity. So when the exponent of a trig function is reduced by an identity, we refer to that identity as a reduction identity. Okay, so on that sheet I shared with you on the 5 part 1 assignment, you saw all the families of trig identities. Among those, you saw the sum and difference identities. Now, one thing you should know, addition is commutative and associative. So sometimes these are written in a slightly different way. A sum, for example, I can invert that and it's the same value. So sometimes on one sheet or another, those values will be switched. Doesn't change the result. So be aware of the commutative and the associative properties of addition. Can be used to write these slightly differently, but it all comes out the same. So one thing to be conscious of, though, wherever you use the identities from, probably a good idea to be consistent. That'll just help you remember them better. So exact value of cosine of 75 degrees. Rowdy is 75 degrees on the unit circle. Yes. Well, be careful. So you got 0, watch me now, 30, 45, 60, 90. It's 75 on that list. No. So we can't know it exactly from the unit circle. But we can know it exactly by using the values on the unit circle as a sum or a difference. So we need to find sum alpha plus sum beta that equals 75 degrees, where alpha and beta are both on the unit circle. So Holden, what's two values on the unit circle that add up to 75? 30 and 45. Very good. So you see how alpha should be 30 and beta should be 45. Or, you can switch those around. It don't matter. So let's apply the cosine sum identity. So that's here. The fact that I don't have these memorized should be a testament to their obscurity. So we want to rewrite I wonder why I do that. It keeps the window from collapsing itself. Okay, so we want to know the cosine of 75 degrees, which is also the cosine of 30 degrees plus 45 degrees, where 30 is alpha and 45 is beta. And so that's equal to cosine alpha, cosine beta, minus sine alpha times sine beta. Okay, unit circle quiz time. Rachel, what's cosine of 30? Without looking. So you're giving me a radian measure, but what I'm looking for is where that point is. There are two values, an x and a y. The x is the cosine, the y is the sine. So we're dealing with these 2 points, 30 degrees and 45 degrees. That's the angle that we've rotated through to get to that radial arc. And by means of those mechanisms I showed you, triangular analysis, we can know that the x-coordinate on the unit circle where that triangle meets the circle is the cosine of the base angle theta, and the y-coordinate is the sine of the base angle theta. So if we look at just these 2 points that we're talking about, 30 degrees and then 45 degrees, we've got this. So tell me what the cosine of 30 degrees is. Okay, so that tells me you need to study the unit circle like the desert needs rain. You're so unfamiliar with it, it's like you never even looked at it. And it's the fundamental idea of this chapter. So look at it. Righty, what's the cosine of 30 degrees?
Square root of 3 over 2.
Very good. That x-coordinate that is associated with that radial arc. And then, Colby, tell me what the cosine of 45 degrees is.
Square root of 2 over 2.
Very good. So right here, we've got the square root of 2 over 2, comma, radical 2 over 2. And you correctly identified positive square root of 2 over 2. And then, Clay, tell me what the sine of 30 degrees is. Very good. And then, Colin, tell me what the sine of 45 degrees is. Excellent. So multiply through here. Square root of 6. Remember that the square root of a times the square root of b is equal to the square root of a times b. Everybody with me on that? So radical 3 times radical 2 is radical 6. And then 2 times 2 is 4 minus radical 2 over 4. This is a, perfectly legitimate answer, but for whatever reason, we usually combine the two. So there's our 75%. There's our final answer, the exact value. Let's check ourselves, shall we? It's the decimal approximation, and I need to go to degree mode, which I'm in. So let's do cosine of 75 degrees. So it's that, and let's see if this is the same. Square root 6 minus square root 2 divided by 4. Yes. Okay, so that's the exact value of cosine 75. So you see how we can now use the sum or difference identities to extend our knowledge of exactness out to anything that is either a sum or difference of values on the unit circle, which is a much larger range of, and eventually, this is, the tables of values that used to be used exclusively in trigonometric work were developed by just this process, using identities to extend your knowledge of exactness. Calculators didn't exist hundreds of years ago, so people had to find these values by hand. This is the mechanism they used to do it. Okay, so tangent of 11 pi over 12. The difference here is we've got radians, And I don't know if you're like me, but I think in degrees. It's like learning the second language. You always think in your first language. So it's very challenging for me. And also, you got different denominators and so on. It can make it a pretty large challenge to determine a sum or difference value from a radian. So what I always do is this, unless it's just obvious. Sometimes it's obvious, but in this case it's not. So I'm going to multiply this by 180 over pi to get my corresponding degree value. It'll be just less than 180, I think. So these cancel. And let's do 11 times 180 divided by 12. And change that to the lowest possible fraction, 165 degrees. So what two values on the unit circle add up to 165 degrees, Mason?
120, 45. Like, can you do that? Or just
Yes. So there will be numerous answers. And this is I could write differences that are 165, but the one you said works perfectly. So 120 degrees plus 45 degrees equals 165 degrees. So we're going to let alpha equal 120 and beta equal 45. And we want the tangent sum formula. So let's go back to our formula sheet here and get the tangent sum. Notice these are formatted a little differently than the cosine and the sine sum and differences. Also, I think on your little special sheet, there's something that could be confusing. It lists these two together, and it's got a little plus minus here. So the symbol on top goes with the symbol on top, and the symbol on bottom goes with the symbol on bottom. That's the sheet that I attached to your 5-part 1 work. You'd think that would be intuitive, but sometimes it's not. Okay. So there's our formula that we want to plug this into. So we want to find, and I'm going to change these back into radians. So this is 2 pi over 3 plus pi over 4 equals 11 pi over 12. So I've got the tangent of 2 pi over 3 plus pi over 4. You see how that's like this, is equal to the tangent of 2 pi over 3 plus the tangent of pi over 4 divided by 1 minus the tangent of 2 pi over 3 times the tangent of pi over 4. So once again, we want to find these exactly, but the tangent is not explicit in the unit circle. In other words, there's not a place where you can see the tangent.
How did you get a subtraction sign? I see on this worksheet it has like a plus and a minus.
So that's what I just discussed. On the worksheet, you've got both listed in one spot. You've got a plus and a minus. Whatever the uppermost symbol is corresponds to the uppermost symbol in the formula. Whatever the lowermost symbol is corresponds to the lowermost symbol in the formula. Good question, Clay. I knew that was going to confuse people. That's why I mentioned it. Okay, but with the sum of tangent, the denominator has a difference. So mental note there. Now, tangent of 2 pi over 3. Let's start with that one. Reciprocal identity. The tangent is equal to what, Riley? Blank over the blank. Excellent. So we've got sine of 2 pi over 3 over cosine of 2 pi over 3. And then on the unit circle, Ian, what is the sine of 2 pi over 3? So you're giving me a degree measure, which is also a mistake that indicates your misunderstanding of the unit circle is complete. That couldn't be a more incorrect answer. So tell me what the sine, the y coordinate associated with that point is. Very good. Square root of 3 over 2. So that's our numerator. Then our denominator is the cosine of 2 pi over 3. So Mackenzie, tell me what the cosine of 2 pi over 3 is. I'm going to roast you guys on this unit circle hard until you get it. So just be prepared. If you don't know it, prepare to be roasted. You're going to leave here crying every day. Yes. Not a lot of confidence in that answer, but it is correct. Negative 1/2. It is the x-coordinate of the radial arm associated with this angle. So if I go to 2 pi over 3 on the unit circle, the x value is the cosine, the y value is the sine. It should take you 0.01 seconds to do that. If you can't, then you don't understand it. You need to study it. So if I multiply top and bottom by 2 here, which is perfectly legitimate, that's going to be square root of 3 over negative 1, which is negative radical 3. So the tangent of 2 pi over 3 is negative radical 3. Now let's calculate, this is just kind of a little aside here. I'm just doing this because we don't know the tangent exactly on the unit circle. We've got to use this reciprocal identity to find it. Now let's talk about the tangent of pi over 4. So, as Riley says, that's the sine over the cosine. And Bristol, tell me what the sine of pi over 4 is. Yes. So square root of 2 over 2. And then tell me what the cosine of pi over 4 is. Hold. Good. So what's anything divided by itself? 1. So we've got the tangent of 2 pi over 3 is this. The tangent of pi over 4 is this. We'll plug them in here. And we're going to have a nice little simple expression. So we get this. And usually it's written like this. So that is the tangent of 11 pi over 12. Let's check our answer again, because that's important to be able to do that. So let's go to radian mode, because this angle is in radians. So we've got the tangent of 11 pi divided by 12. So that's this decimal value. And let's see if it corresponds to what we found. 1 minus the square root of 3 divided by 1 plus the square root of 3. Sure enough. So this is the exact value of the tangent of 11 pi over 12. The radians, again, can be tricky. You will have a test or a quiz problem on this. And if you don't know the unit circle, it's not going to happen. You guys are testing my patience with this unit circle stuff. It's not rocket science. So here's one for you. See if you can figure it out. Find a sum or a difference that has 15, and then apply the appropriate formula. Put this up here in case you guys. That's the one I would use for this. Not the only possible. You could use the sum instead if you use the negative angle, but it's up to you guys. Campfire at night. Crickets serenade us. You know what that is? It's an insect announcing its desire to mate. Yeah.
You can enlarge that version.
It's about the best I can do. Yep. Correct. Possible. Good question, but it's possible. Seems like something might be wrong with this.
Probably.
That's okay.
Or I just got crappy batteries.
That could be as well. I'll go to Amazon. I don't really get one. You're welcome. All right, so let's talk about this. Colby, what did you choose for alpha and beta?
45 minus 30.
Quiet, please. Quiet, please. Quiet, please, gentlemen. Come pay attention to me. So that's a good choice. You could also use 135 and 120. A lot of different ways you could approach this problem. In fact, an infinite number of ways because of the infinite number of coterminal angles. Question?
I was just going to ask, would it look different if you use different angles?
The result would be the same.
Yeah. But
This expression would be different until you simplified it, yes. Once you simplified it, it would be the same value. All right, so if we plug that in, we get the tangent of 45 degrees minus the tangent of 30 degrees over 1 plus the tangent of 45 degrees times the tangent of 30 degrees. And what does that simplify to, Kobe?
1 minus radical 3 times 1 plus 1 minus radical 3, which would be radical 3.
So let's see if that corresponds to the value of tangent of 15. So am I in degree mode? No. Always check your mode. That didn't make sense to me. That's why I knew that. But you guys probably haven't fooled with these enough to know what makes sense and what doesn't. So double check your mode every time. So this is what the ratio should be. And I think you're going to have the additive inverse. But let's see. So the square root of, well, let's do 1 minus the square root of 3. And then 1 plus the square root of 3. Yeah, see how it's positive and negative? What we actually should get, and I'll show you, the numerator's a little off. So this is 1 minus, and then the tangent of 30. I think maybe the denominators make where the difference comes in. Anyway, so the tangent of 30 is the sine of 30 over the cosine of 30. And you see from here that's 1/2 divided by square root of 3 over 2, which is 1 over the square root of 3, which is radical 3 over 3. So 1 minus radical 3 over 3 for the numerator. And then for the denominator, it's 1 plus 1 times radical 3 over 3. Usually don't leave a complex fraction in place, so I'm going to multiply through by 3. So let's see if that corresponds.
I think for tangent of 30, you get 1/2 over radical 3 divided by 2, but it's radical 3 divided by 2 over 1/2.
Well, this is right, and let me explain why.
Okay.
So remember the tangent is the sine over the cosine. And what you just said is a pretty classic mistake because intuitively, for some reason, you want to put the first thing here as the numerator. But remember that it's sine over the cosine, where the sine is the y value and the cosine is the x. So the second thing listed in this case is the numerator, and the first thing is the denominator. I appreciate you voicing that, though, Clay, because that would be a common misconception. And if you got it wrong, that's probably why. That's probably why. So here's what we're looking for. And this is another way to say it, but this would be fully simplified. Okay, so a little practice with those. So sum and difference identities are used a lot in electrical engineering. So electrician is a good job that pays well. I think the average salary in Johnson City is about 60 grand, which is nothing to sneeze at. So what most school teachers make. So, and we went to school for a long time. I went to school for 6 years. I'll probably make just barely that. The electrical engineer goes to school for a year and change. At least an electrician, a standard practitioner. You can get a 4-year degree in it, but I think that if you go to PCAT and do their electric program, it's a year and change. Anyway, you can go straight into a $60,000 a year job. One of the things they use to determine the current in a circuit are formulas like this that involve trig functions. Now, one thing you have to be conscious of in electrical engineering or electrical circuit analysis, I no longer means the imaginary unit. So I is current and J is the imaginary unit. So each subset of the science family has their own little pet notation for things. So you're going to become accustomed to this. Physics, for example, has their own little pet notations. They love subscripts in physics. If you guys have ever taken physics, the subscripts are everywhere. And you'll have like 3 different values in the subscripts. It's extremely confusing. But in electrical, they change I to mean current, and J is now the imaginary unit. Not going to apply here, but worth noting. Okay, so it says, rewrite the formula in terms of the sum of 2 angle measures. So we've got I equals 4 times, and they really need parentheses here like the desert needs rain. Otherwise, it doesn't make much sense. If the T is part of the argument, you're not simplifying anything. So it clearly has to be outside the argument. So I here is the current, and it's 4 times, and I can rewrite that as the sine of 225 plus 30. Yeah, those are 2 values on the unit circle. And now we need the sine sum formula. So let's go back here and get that. So we're going to apply alpha is 225, beta is 30. So the sine of 225 is negative square root of 2 over 2. If you don't know that, consult your thing. Unit circle. So that would be the first term here. Negative radical 2 over 2, that's sine of alpha, times cosine beta. So the cosine of 30 degrees, the x-coordinate at 30 degrees, is radical 3 over 2, plus cosine of alpha, which is also negative radical 2 over 2, times sine of beta, which is 1/2. So if I multiply, well, let me combine these fractions first. See, when I multiply through by 4, all the denominators are going to cancel out. And there you've got a much simpler formula. So you see, if you're an electrical engineer or an electrician, it's going to be a lot easier to work with this because you don't need to worry about a trig function. Persistent little cricket. I usually hear him in the teacher's lounge. That's where he likes to live most. Curious that he has followed me here. Universe is trying to send me a message. Maybe like when I ask you a question about the unit circle, I hear. What's that?
Maybe it's Jimmy Cricket on your.
Could be. Tell me to when I wish upon a star. Okay, so this is the same question basically. We don't need to do another one of those. Let's find the exact value. So this is a little different. So here they're asking us to apply that identity in reverse. Okay, so it looks crazy, but it's actually not too strange. So what we've got here is one of those formulas related to the tangent. We have to figure out which. And where alpha is 78 and beta is 18. So notice it's a difference in the top and a sum in the bottom. So if I look over here, that's the difference, tangent difference. So I know that I need to apply the tangent difference to this problem. And so that's going to be tangent of 78 degrees minus 18 degrees, which is the tangent of 60 degrees on the unit circle. Sine of 60 degrees over the cosine of 60 degrees. Jesse, what's the sine of 60 degrees? So the sine is the y-coordinate. Good. I'm a lot less upset by picking the wrong value than I am by giving me a radian measure. Okay, so Caitlin, what's the cosine of 60 degrees?
1/2.
Excellent. So if I multiply top and bottom by 2 here, get that answer. Relaxing. Okay, so another one. What to flip? Well, it's clearly one of those sum or difference with the sine and the cosine. We've got sine, cosine, cosine, sine, and it's got a plus sign between it. Let's see what that looks like as far as our formulas go. Sine, cosine, cosine, sine. Right here. Sine sum formula. All right. Wrong one. There we go. So you see how that matches? If I let alpha be pi over 3 and beta be pi over 4. So I can rewrite this as the sine of pi over 3 get there eventually, plus pi over 4. So there's probably some, it might be on the unit circle, let's see. So pi over 3, 3 and 4, least common denominator here would be 12, I believe. So that's 4 pi over 3 plus 3 pi over, I'm sorry, 4 pi over 12 plus 3 pi over 12. And that is 7 pi over 12. Not on the unit circle, so just double check myself here. So not on the unit circle, meaning we can just work it out this way. So that is sine of pi over 3. I think maybe they want you to just give this answer. But it's also the case that we can resolve this pretty quickly. The sine of pi over 3, go with pi over 3, the y coordinate there, radical 3 over 2. Cosine of pi over 4, radical 2 over 2, plus cosine of pi over 3, 1/2, sine of pi over 4, radical 2 over 2. So that's radical 6 over 4 plus radical 2 over 4, which is radical 6 plus radical 2 over 4. So not really absolutely sure which answer they're looking for here, but either one holds true. Okay. Don't want that one. Let's talk about this one. Example 4. So write this as an algebraic expression of x that does not involve trig functions. Oh yeah. Here's where it gets fun. Cosine of arc sine radical 3 over 2 plus arc cos x. Yeah, baby. We're going to make 2 reference triangles. So this is just some angle alpha, okay? And in that angle's corresponding triangle, the sine, in other words, the ratio of the opposite to the hypotenuse is radical 3 to 2. So I know the arc sine of that the alpha comes from has this for its reference triangle. So if I use the Pythagorean Theorem, I'm going to get 1 here. So square root of 3 squared is 3, 2 squared is 4, difference is 1, square root of 1 is 1. Applying the Pythagorean Theorem. So what we need is the cosine, and that's alpha. We'll need all this information. Remember also that this is the cosine of alpha plus beta, so you kind of see where I'm going here. I'm going to use that formula in just a second. But I need to know some more about beta first. So beta's reference triangle has a cosine ratio of x, or x to 1. So the ratio of the adjacent to the hypotenuse is x to 1. Now I'm going to use the Pythagorean Theorem to find that unknown side. So I've got x squared plus something I don't know. I'll call it b squared equals 1 squared. So x squared plus b squared equals 1. B squared equals 1 minus x squared. And b equals the square root of 1 minus x squared. Just consider the negative root because we're talking about distances, which cannot be negative. So this reference triangle for beta looks like that. So now we know everything we need to know about alpha and beta. Let's apply that formula. So once again, go back to our formula sheet. And we want the cosine of alpha plus beta. That's the upper left here. All the way back to where we were. So cosine alpha plus beta. So we want cosine alpha. I'll look up here at alpha. The cosine adjacent to hypotenuse is 1/2. The cosine of beta. If I look here at beta, the cosine is x to 1 or just x minus sine alpha, opposite over hypotenuse, radical 3 over 2. And then sine beta, opposite over hypotenuse, like that. So we just simplify this expression. So I've got a couple ways I can do this. So that's x over 2 minus radical 3 times radical 1 minus x squared over 2. Then I can use the root property, product property of roots, to get this. Then I can combine the two and get this. It's important to know how to do all this because sometimes on those multiple choice tests, they'll simplify it fully. Sometimes they'll leave it at some intermediate point. But there's not a lot of consistency there.
Wasn't that saying too?
Oh, thank you, Holden. Yes, you're right. Let's see. Entire page? Yes. No, that's hard to see, but impossible to get it all up there without making it tiny. Anyway, as I continue simplifying there, that was just to help you understand what might be necessary to match a multiple choice answer. Also, this one has an X in it, so you can't do it. But if it doesn't, you can convert it to a decimal, convert all the answers to a decimal, compare. That's a great ACT strategy. I mean, there's an ACT retake coming up for some seniors, I think. So if you guys are in that category, commit that to memory.
So we don't even have to find arcs on it.
No, there's just some angle alpha, some angle beta. And we use this, the cosine sum formula, just to make our life easier. Okay, good question. So here's the book's reference triangles look different, but the values are the same. So, I don't think we need another one of those. So verifying cofunction identities. This one is, you notice I've already got it written up here. That's because it's a very counterintuitive problem. In other words, verifying a cofunction using a sum or a difference. Well, here's one way you can do it. Let 0 be alpha and negative theta be beta, which nicely rhymes. And then you plug them into the cosine difference formula, and you'll get this verification. So this is an example of using one identity to verify another. Each identity is built on the last, in a sense. You have to have ways to develop these. These didn't fall out of the air. And what happened was the identities were all developed from each other slowly over the course of years of analysis. Now, you know, self-discovery is a big push in education. People in education, well, they really don't have enough to do. If I'm being honest. Education is kind of a jobs program by the government for overeducated adults. So a lot of people in the field of education don't have enough to do. And so they preoccupy themselves with reinventing the wheel. In other words, coming up with new ways to teach. And interestingly enough, the greatest theorists in this field, in general, have never taught a class. They just think about teaching classes. So if I were to think about playing soccer, how good of a soccer player would I be? What if I did nothing but think about it? I'd be probably better than somebody who hadn't, but I would not be as good as somebody who had practiced the art. And so here we are, beholden to folks that have no practice in teaching. And they constantly come up with these notions. And one of the notions is self-discovery. Some of the greatest minds in history discovered the principles I've shown. In this case, Euclid, perhaps the greatest mathematical mind ever exists. Are you just going to happen upon principles that Euclid discovered? No. Sorry. You might be smart, but you're not that smart. It just ain't going to happen. So the notion that we can discover these principles is kind of ridiculous. But there's a push in education to teach that way, to just help you happen upon the discovery of these mathematical principles. Doesn't work. I tried it. But anyway, so I'll give them to you cold. But the process of development and discovery is interesting, should you want to look into it. Here's another one. Works out the same way. Not really worth your time. So this is an interesting problem. You might think cofunctions, because we're adding an angle here, but actually the sine sum and sine difference is what we want to apply here. So let's go back and get those. Here we go. So these are the two formulas we're going to use. And do you see how this is like this and this is like this? Let's see where I'm going with this. So in the case of the left one here, the one I've highlighted in green, the alpha is x and the beta is pi over 4. So I can rewrite that as the sine of x times the cosine of pi over 4 plus the cosine of x times the sine of pi over 4. So I'm going to shrink that down a little bit. So that comes from this part. And then we're going to subtract away this expression, which in this case, the alpha is x. And the beta is also pi over 4, so same as the first one. So let's see here. Sine x times cosine pi over 4 minus cosine x sine of pi over 4. And we're going to be subtracting that again. Make sure that's root. Not. This pi's hat there. A big fancy hat now. So that's going to be equal to 0 is what we want to solve. So I put in both of those, and it's important for us to remember that that negative sign is distributed to both terms on the right. Easy to make a sign error there. So the sine of x times cosine of pi over 4 is radical 2 over 2 times sine x. Usually we put the coefficient in front of the trig function. And this is going to be radical 2 over 2 cosine x minus radical 2 over 2 sine x. And then minus a negative is plus radical 2 over 2 cosine x. So some stuff cancels here. Tell me what cancels. I can't do.
The radical 2 over 2 sine x and negative radical over 2.
Excellent. These two terms cancel each other out. And so I have 2 times the square root of 2 over 2 cosine x, and 2 times so 2 times the square root of 2 over 2 is just radical 2. See how the 2's would cancel there. And that's equal to 0. Now it's a much more manageable equation, don't you agree? In fact, I can divide away the square root of 2, and I have perhaps the simplest trig function possible. And we're concerned about solutions on the unit circle. So where is the cosine 0 on the unit circle, Riley? The x coordinate. So just go around the unit circle, think about where that x coordinate is 0. There's 2. Say again. That's where the y coordinate is 0. Where's the x coordinate? 90 pi over 2. No, 210 is just past 180. You want to go on down. Take multiples of 90. Go ahead.
270.
Correct. So 90 and 270 are pi over 2 and 3 pi over 2. So let me give you a nightmare scenario. Let's imagine you encounter this on the ACT. What the heck? Mr. Sayer said something about this a long time ago, but I blocked it out then, and I certainly don't remember it now. So what you can do is use your graphing calculator, which you can use for the ACT, and make sure we're in radian mode, because we are inputting radians, first of all. Second of all, we're graphing. So both of those things necessitate the use of radian mode. So the sine of x plus pi over 4 minus the sine of x minus pi over 4. And then if I graph that on a window from 0 to 2 pi, which I've already got here, and our y coordinates are okay. We're going to have 2 solutions. See how where it hits the x-axis? Check this out. Trace pi over 2. Boom. What about this one? 3 pi over 2. But that's boring. This is fun. You really going to cop out like that? Well, do what you must. That is it, ladies and gentlemen, for this section. Let me give you a brief summary.
Actually, I'm not finished.
Got to pull up my assignment list. Got behind on my stuff because I had to get all the grades ready. For you guys and your dang makeup work. One more section in chapter 5. Can you believe it? Oh, I meant to tell you, I've revised my plan just a bit. I'll discuss that briefly as soon as I get this done. It's page 341, 1, 2, 9, 11, 12. So 5 problems. Try not to overburden him. All right, so first of all, here's the assignment again. Second of all, my new plan for chapter 5 is as follows. After careful consideration, also I'm going to be out Friday, so I had to think about that. Today's Tuesday. We covered 5, part 4. Wednesday, tomorrow, all we're going to do is a quiz. I'm going to open it up in the morning when I get here. If you guys have any questions, don't understand, maybe there's some technical issue. You know, as good as I am with technology, I make errors. And in fact, I think my proficiency is a bit overblown because in the land of the blind, the one-eyed man is king. And here I am, the one-eyed man, who everybody thinks is so technically proficient, but it's really relative proficiency, not absolute proficiency. But anyway, quiz tomorrow. Thursday, the last section, 5-5. I thought about skipping this. Then I looked at the test I had made, and it had 5 questions from 5-5. And I thought, ooh, that ain't going to work. So 5-5 on Thursday. Friday, we're going to do a study guide in class. You're going to watch a video of me going over the problems on the study test. I'll give you a copy of the study test. And then this weekend, you're going to complete the test. So I'm going to have it open until Monday evening, 11:59. So you'll have Saturday and Sunday to take the test. You want to strike while the iron is hot. I usually give extra day or two, but that can do more harm than good if you wait till the very last minute and start the test under duress. It just makes an already stressful situation worse. Wouldn't you agree? And then next week, Monday, we're going into chapter 6, the light at the end of the tunnel. So that's our tentative short-term plan. As always, subject to change, but that is what I intend to do for the next few days.
So tomorrow for the meet, are we gonna have a good
Say that again.
tomorrow for the meet that we do? Are we gonna have a good during that time?
Yeah, we sound like the.
Yeah, I'll probably do one session in the afternoon, and I'll take homework questions or.
Is that like something that is required of us to still go to?
Yeah, I think you have to pop in for me to count you present. That's one of the rules. Or send me an email explaining why you can't, and then doing the online work. So those are your 2 options. You got to work, or whatever. I understand. I was a kid of limited means. I had to work too, so I am sympathetic to that. All right, let's turn this off.